For an animal to control its movements, it needs to have information about the state of its body. One important proprioceptive variable is the amount of rotation of a given joint. There are typically two different forms of information that an animal might want about the joint rotation. The first is a graded signal that gives it a general idea of how much the joint has bent. The other is binary and just tells it whether the angle has exceeded some threshold value. In this case, the animal might only want to know when the angle reaches its most anterior position. We'll build two simple examples that demonstrate how to reproduce these systems in AnimatLab. Let's begin by creating a new project. Name it Joint Angle. Now let's add a new organism and open its body editor. Create a new root body. Freeze the root so it stays in place. And then let's add the arm. Change its color to green. And reset its rotation to 0 degrees. Next, let's set the size to be 1 by 5 by 10 centimeters, and then change its local location to be 10, 0, 0 centimeters. Last, let's change its name to be arm. Then let's go to the hinge joint and change its name to arm joint. Rotate it around the y-axis by 180 degrees and then set its angular limits to be 45 and negative 45 degrees. Next, let's go back to the camera and set an elevation of 5 centimeters and change the distance to 40 centimeters. This will give us a better view of the movement. Now let's run the simulation and make sure that our joints are moving the right way and that the constraints are correct. Now let's add some motor stimuli to manually move the joint back and forth for our tests. Select the joint and add a motor stimulus. Change its name to A and set the start-end times to be 0 and 3.8 seconds. Set the velocity to be 0.2 radians per second. Now add another motor stimulus and name it B. Set its start and end times to be 5 and 12 seconds and its velocity to be negative 0.2 radians per second. Finally, let's add a third motor stimulus and name it C. Set its start and end times to be 14 and 21 seconds and its velocity to be 0.2 radians per second. Go back to the body editor and select the root node. Change its X rotation to be 90 degrees. Now let's run the simulation again and watch how the joint moves with these new stimuli. Now open the behavioral editor and let's connect the sensory neurons to the body. Add a normal neuron and change its name to be LJA for linear joint angle. Then add a joint node and change its name to arm joint and attach it to the new neuron. An adapter is automatically added for you. Change its name to be LJA adapter. Next, let's set the joint ID to be arm joint. This associates the node to the actual joint in the body. The linear joint sensor produces graded firing based on the angle of the joint. It does this using a linear gain function. The rotation around the joint is related to the amount of current that is injected into neuron LJA. In order for the neuron to be able to report positive as well as negative joint angles, the neuron needs to have a baseline firing rate at 0 degrees. This way, positive angles will increase its firing above its baseline, and negative angles will decrease its firing below that baseline. We'll set the current that produces this baseline value at 5 nanoamps, so we'll have a range between 0 to 10 nanoamps of current injected into the neuron for angle changes between negative 0.707 and positive 0.707 radians. This means we'll need a slope that's equal to 5 nanoamps divided by 0.707, which is equal to 7 nanoamps. Our intercept will be 5 nanoamps. Enter these values for parameters c and d of the polynomial equation in the adapter's gain function. This will produce a firing frequency that is graded based on the joint angle between these two limits. Now we can see that at negative 0.707 radians, the current is 0. At 0 degrees, it's 5 nanoamps, and at 0.707 radians, it's 10 nanoamps. Now let's create a new line chart and add the joint rotation and firing frequency of neuron LJA to the chart. Let's run the simulation again and look at our response. You can see that the firing frequency follows the change in the angle of the joint. Next, let's add sensors that detect when the angle exceeds some threshold. Add two spiking neurons to the diagram. Set the name of the first to be AEP. This stands for anterior extreme position. Set the second to be PEP. This stands for posterior extreme position. Set the initial threshold for both neurons to be negative 50 millivolts. Copy the arm joint node and connect it to each of these new neurons and change the names of the adapters. The limit angle sensors detect when the joint has exceeded some threshold value. It accomplishes this by using sigmoidal gain functions. When the angle goes beyond 0.6 radians, the current injected into AEP increases from 0 nanoamps up to a maximum of 20 nanoamps. Similarly, when the angle goes below negative 0.6 radians, PEP receives injected current. This ensures that these neurons begin firing strongly once their threshold values have been exceeded. Open the gain for the AEP adapter, then select the sigmoidal gain function. Set A to be 0.6, B to be 20 nanoamps, C to be 50, and leave D at 0. The parameter A sets the horizontal offset for the center of the sigmoidal function. It moves the chart left and right. B sets the amplitude of the function, C changes the steepness of the function, and D is the vertical offset that moves the function up and down. Now open the gain for the PEP adapter and set A to be negative 0.6, B to be negative 20 nanoamps, C to be 50, and D to be positive 20 nanoamps. This changes the direction of the sigmoid so that positive current is injected for values less than negative 0.6 radians. Next, let's go back to the line chart and add new items to display the AEP and PEP membrane voltages. Run the simulation again. You can see that AEP only fires once the joint angle has gone above 0.6 radians, and PEP only fires when the angle goes below negative 0.6 radians. These are two ways in which you can feed back information about joint angle into your neural network. I hope this tutorial has been helpful.